All right, graphs of the 6 trig functions. We're just going to recap some of the key concepts from each of the functions. Notice we have y equals sine x for the first one. Let's talk about the domain. Now, I haven't emphasized this yet. We've just been focused on one period. But remember that this period can continue infinitely to the left, and sine can continue infinitely to the right. So we say that the domain is negative infinity to infinity, remembering that we can't include infinities, so we have parentheses rather than brackets. Now the range for sine is -1 to 1, and it actually gets there because remember this is defined from the unit circle. So we have -1 to 1. The period, remember sine is defined from the unit circle, so the period is just 2 pi because it takes a complete circle to complete a period. Now the intercepts get a little trickier. We have to talk about all the different places where sine crosses the x-axis. Now there's an infinite number of places, but not all points are obviously the intercepts. So how do I label these efficiently? Notice we have 0, pi, and 2 pi are the first period of intercepts for sine, including -pi if we go backwards, and -2 pi, and so forth. Notice this is every integer value of pi. So if I wanted to label this out, I would say n pi, given that n is an integer. These are the x-intercepts. Now the y-intercept for sine is just 0, 0, because it crosses right here. Now is this even or odd? If you guys remember from even and odd functions, if this function can be flipped this way and come back on itself, then that is an odd function. So sine is in fact odd. And the symmetry is about the origin. Okay, anytime graphing transform sine functions, we have to reference each of these things, characteristics about the sine wave. For cosine, very similar. A lot of these things are the same. Notice this goes on forever left and right. So the domain is -infinity to infinity. The range, just like the sine wave, goes from -1 to 1. This is the y value, and it includes it. The period, remember cosine is defined from the unit circle, and it doesn't repeat until it completes the circle. The x-intercepts, though, are a little trickier. Notice this is pi over 2, this is 3 pi over 2, and so forth. And we have -pi over 2 and -3 pi over 2. If I wanted to label this efficiently, notice it's between these two different intercepts, there is a pi added to it. Notice between these two intercepts, a pi is being subtracted from the pi over 2. So we're adding whole number values of pi, or we're subtracting integer values of pi. So an efficient way to say that is pi over 2 being the first one in the first quadrant, plus n pi, because we're adding integer values of pi. Notice we're talking about intercepts here. Let me clean up my drawing. Oops. I'll just write that. All right, the y-intercepts, note that it's just simply where it crosses the y-axis. That's 0, 1. Is this even or odd? Remember that an even function can map itself if you just reflect it over the y-axis. This is even, whereas sine was odd. And the symmetry is, therefore, the y-axis. All right, let's move on to tan. We have y equals tan x. Remember the key concepts from tan were the asymptotes, intercepts, and the quarter and three-quarter mark. I have scaled this a little bit differently. Notice I've scaled it by pi over 4. I'm just going to skip every other one where pi is over 2, pi, -pi over 2, and -pi. Now the asymptotes occur for tangent at -pi over 2 and pi over 2. Intercepts at 0, -pi, and pi. And the quarter marks, which we use for graphing, are -pi over 4, -1, pi over 4, and +1. And we just draw a smooth curve between them. Now the domain in this case is all real numbers except the asymptotes, because remember a function plot can't cross its asymptote if it's vertical. It can cross a horizontal asymptote, but not a vertical asymptote. That was messy. So let me just go like this. Whatever. All right. So if I was looking for the domain, it's everything other than the asymptotes. So x not equal to. Now how do I say the asymptotes efficiently? Notice the first asymptote occurs at pi over 2. The other asymptote occurs a pi away from it. Notice this is a pi distance away in angle. So the next one's going to occur a pi this way. So it's integer values of pi being added to pi over 2. So it's x not equal to pi over 2 plus integer values of pi. The range, notice this goes forever down and forever up, so it's all real numbers. And but it's preferred to write it as an interval notation, negative infinity to infinity. The period, remember tan, just a quick talk about this. Remember tan is defined as taking the y value and dividing by the x value. The signs in the first quadrant make tan positive, and in the second quadrant it's negative positive. This would make tan negative. In this quadrant it's negative negative, which means it's positive, but all the values are the same as the first quadrant, so we are repeating the values from the first quadrant. And so forth for this one, because this is positive negative. Now this is repeated from this one. So the period for tan is pi. X-intercepts occur at 0 and pi. In fact, just integer values of pi. Y-intercepts, the tan graph crosses the y-axis at 0, the origin. Vertical asymptotes are the same thing as the domain because you can't cross vertical asymptotes. Even or odd, and the question we're asking here is, how can we map this graph onto itself? Let me erase some of this. It's getting messy. How can we map this onto itself? If we reflect over the y and then over the x, do we get the same graph? And in fact, we do. This is an odd function. That means it has origin as its symmetry. Going to cotan. Cotan, very similar to the one before, except our asymptotes change, pi over 2, pi, negative pi over 2, and negative pi. The asymptotes occur at 0 and pi. In fact, integer values of pi. So the domain is everything other than integer values of pi. Integers are all the whole numbers plus their negative opposites. Range, same deal. It's forever up and forever down, so it's negative infinity to infinity. The period, just like tangent, is pi, just like tangent of pi. And the x-intercepts occur at negative pi over 2 and pi over 2. So if you note, that's the same thing as what happened, that's the same thing that happened with the asymptotes of tan. So this is pi over 2 plus integer values of pi, because we're adding pi's every time. The y-intercepts, there's a y-asymptote, excuse me, an asymptote at x equals 0, so there is none. And yeah, it doesn't even say it in there, so there's none. Vertical asymptotes occur where x, what's restricted in the domain, so x equals n pi. And we're looking for even and odd. If I were to reflect this across the y-axis, if I were to reflect this value across the y-axis and then across the x-axis, I would end up back where I am from the beginning. So this is an odd function, which means the origin is the symmetry. This graph is the cosecant graph. I know that because sine starts and stops on its axis. I've scaled this by pi's over 2. Now, focusing on the cosecant graph, that's this purple graph right here, not the black graph. I use the sine as the reference for creating the cosecant graph because the intercepts of the oscillating axis for sine are the asymptotes of cosecant. And then the extrema for sine are shared between the sine and cosecant graphs. So minimums and maximums, it just changes from a minimum to a maximum and a maximum to a minimum, and so forth. Now the domain is all values except where it crosses its where sine crosses the oscillating axis, which if you notice is 0, pi, 2 pi, and so forth. So x cannot equal integer values of pi. Now the range is not all real numbers. It's all real numbers above 1, including 1, and all numbers below negative 1, including negative 1. The way we write that is negative infinity up to negative 1. We write a union, meaning these two things are included. And it includes, oops, this was included, so there's a bracket. It includes 1, and it goes off to infinity. The period is how often this repeats. It goes with sine, therefore it's 2 pi. X-intercepts, there is no x-intercepts because it can't be between negative 1 and 1. Move this over. So there is no, there are no x-intercepts. y-intercepts, there is an asymptote, a vertical asymptote at the y-axis, so there is none of that as well. Vertical asymptotes occur where the domain is restricted, so it's the vertical axis, every integer value of pi. Now, even odd, we're asking if we were to reflect this across the y-axis and then across the x-axis. Notice that does map it on itself, so that is an odd function. And the symmetry means, therefore, that it's symmetrical about the origin. And the last function is secant. Secant goes with cosine. Cosine starts and stops on its amplitude. Starts and stops on the amplitude, and the asymptotes occur where cosine crosses its oscillating axis, which in this case is the x-axis. They share the extrema, like I said before. So we take that and let's analyze the graph. The domain is where x cannot equal in this case, and it cannot equal the asymptotes. So we're going from pi over 2 to pi over 2 to 3 pi over 2 and so forth. So we're adding integer values of pi to pi over 2. Integer values of pi. Now the range is the same as that of cosecant. Whoops. So negative infinity to negative 1, including negative 1, so it's a bracket. Then from 1 to infinity. The period, just like cosine, is 2 pi. X-intercepts, there are no x-intercepts. But there is a y-intercept, and that's at 0, 1. Vertical asymptotes occur where cosine crosses the oscillating axis, which is at pi over 2 plus n pi. If we were asked to say if this is even or odd, if I reflect this about the y, it maps onto itself, so it's an even function, and its symmetry is the y-axis. That's it. That is all the 6 trig functions and all their different concepts associated with it. You need each of these concepts in order to be able to graph transformed trig functions.